this generating function. Okay, now let's write out explicitly what is v of r. So here we see that the first term is what we discussed, the monopole term, and the second term is a potential for a dipole term, and the third term is a quadrupole term. Notice that they are ordered by 1 over r. Now we can check that this expansion actually really works by comparing the simple dipole model. So for this problem of a dipole made of 2-point charges, we've done the calculation before, and if you do a Taylor expansion of the field far away, we can get the final answer as qd cosine theta over r squared times 1 over 4 pi epsilon naught. And now for this, using the formula above, we can simply plug everything in here, and let's check. So here, this r cosine theta prime is equal to a constant if we are looking at the far field limit, and then this r prime is d over 2 for the positive charge, and minus d over 2 for the negative charge. And now if we sum them together, it's dq cosine theta prime, and then the VR is simply the dq cosine theta prime times 1 over r squared and 1 over 4 pi epsilon naught. The two actually agree with each other. Now here I'm actually trying to calculate the giving an example and calculating the multiple expansion term by term. So here the charge density I'm trying to look at has the form of k r over r squared times capital R minus 2r times sine theta squared. Here this r is the radius of this sphere, and now if I expand, what I'm trying to look at is the field along the d direction. So I'm expanding the monopole term first. The monopole term is simply the entire charge distribution and integrate over all space, and adding this volume element. Now the integral can be separated into the radial and the angular part, and also the phi direction is simply gives us 2 pi, which cancels out this 4 pi and gives us 2. And the radial part integrated out to be 0, so there are no monopole in this problem. And then the dipole term, we can do the same thing, except that when we need to multiply this r prime cosine theta prime for this dipole term, and also change the order to r to the square. And this time, if we separate the radial and angular parts, we actually find that the angular integral goes to 0. So the total dipole contribution is still 0. Then this means that we have to go calculate the quadrupole term. And the quadrupole involves r prime to the power of 2, and this is p2 cosine theta prime, and also the r is raised to the power of 3. Now if you follow through the calculations, you can get the end result, that is some constant and times 1 over r to the power of 3, because I'm looking at the z direction, so this r to the 3 is replaced by z to the 3, and all this cosine theta primes evaluate to be 1 because of this along the z-axis. Now, here this is simply a copy of our previous derived result, and I actually want to emphasize that we can reinterpret this distribution as the following. So instead of doing all these integrals at the same time, we can actually separate them into two parts. So what I mean is that here for the first type, for monopole term, we define this q as the monopole moment, and now our v monopole can be expressed compactly as the q over r. This is simply the potential for a point charge. Now we can actually define a similar thing for this dipole term. So here this is the dipole expression, and now we can identify that this alpha is the angle that depends between the r and r prime. Here, this cosine alpha could be expressed as r prime dot r hat, which gives r prime cosine alpha, and using this identity, the r prime, because the r hat does not depend on this r prime, so we can pull that out of the integral, and this gives the integral of the simple term, and also there is a hat dot r prime term. And now we can define this r prime integral as the dipole moment p, and then the dipole potential is also simplified to be the term over here. We see that here the dipole moment potential is an analogy to this monopole moment potential. Now the analogy for this point dipole, for the point charge, here becomes a point dipole. And what I mean by point dipole is that here we can have two point charges that's separated by separation vectors, say d, and a point dipole really is keeping this dipole moment the same, but the separation distance go to 0, and for this point perfect dipole, this dipole potential is exact. So we can compare this pure or perfect dipole on the left, and the potential for a physical dipole on the right. And you can see that in the far field these are identical, but in the near field the point dipole or the pure dipole is different from a physical dipole. Now what I want to mention here in the multipole expansion that the origin of the coordinate may play some role. So here, for example, if I consider this monopole term, this say there is a charge distribution, the monopole moment is Q, is simply the total charge that do not depend on the origin of the coordinate. And if you calculate the dipole moment of a point charge, you actually see that that is QR d tau. Here, for a point charge, this is simply Ri times Qi. And for a single charge, you can see that this actually depends on where your origin is. So for the multipole expansion, only the first term is independent coordinate you choose, and the dipole term already depends on where you choose your coordinate, and also the same for the quadrupole terms. And only if you choose the origin to be exact same as your point charge, all your higher order terms go to 0. And if you slightly shift the origin, there will be higher order term. And now let's check what's the case for a dipole where the total charge is 0. So here what I consider is plus Q and minus Q. So for this dipole, the first order monopole term is 0. And now if we calculate this dipole moment, here this dipole moment actually say we choose our origin, and this dipole moment for this special case where there are total 0 monopole equals to this R plus minus R minus times Q, where this R plus minus R minus is simply the separation vector between the two. So we can see that this is actually again independent of this origin of your choice. So it means that really in the leading order, where the multipole expansion is non-zero, and then this term does not depend on the origin of your choice. And there are more physics in these leading terms, and the higher terms might be some mathematical consequences of the origin of the coordinate of your choice. Finally, I want to mention that we actually derive these dipole potentials in the homework. If you still remember that we actually calculated the case of two charged sphere that's separated by a distance d. However, in this homework, we define the d to be pointing from the positive charge to the negative charge, where a more conventional calculation of a dipole moment for this case will be this d times q. And so for that, if you replace minus qd by this p, you will see that the dipole potential will, in the homework, will look like the form over here. And in the homework, we also calculated the corresponding electric field, and we will use this in the next homeworks, in homework 3.